In this video, I'm planning on talking about specific heats and using them in the first law equation for solids and liquids. So in the previous video, I talked about specific heats and how those are used to solve first law problems, assuming you have an ideal gas. So this time we want to, and remember, if we had the first law problem, so let's say we have Q minus work is equal to delta U plus change in kinetic energy plus the change in potential energy. So really what we're trying to do here is solve the first law equation, and we're trying to get either delta U, or in the case of boundary work, delta H, in the case that we can't look these values up on a thermodynamic table. So if we can look delta U, or if we can look up U2 minus U1 or H2 minus H1, like if we can look these up on a table, that's what we're going to do. But if we don't have the data available for those, then we're going to need to calculate what they are, and that's where we're using the specific heats. And so in the previous video, I went through how to solve for delta U and delta H, assuming that you have an ideal gas using specific heats. And in this video, we're going to look at how to solve for delta U or delta H, assuming that you have a solid or a liquid. And so coming back to specific heats, first of all, specific heats are simply a property, just like any other thermodynamic property. So, and if you remember from the previous video, C sub P and C sub V can be used for any process. So these can be used for any process. So we've already looked at how to use these if you have an ideal gas. And so what we want to do, so in this video we're looking specifically at solids and liquids. So first of all, so remember that enthalpy is equal to the internal energy plus the pressure volume work. And so dH is equal to, du plus dPV. And then we want to use the chain rule on this. So I'm going to apply the chain rule to this, and we're going to get that dH is equal to du plus P dV plus V dP. Let's just rewrite this. So we have that dH is equal to du plus P dV plus V dP. So now what we can do, so first of all, we know that we have a solid or a liquid, and we know that for a solid or a liquid, we're going to assume that they're basically incompressible. So this is a pretty good assumption for a solid or a liquid, and if the solid or liquid is incompressible, this means that dV is approximately 0. So in other words, this term basically goes to 0. And then the other thing that we can assume is so looking at this term, and we're going to come back to this in a minute, but looking at this term, we're going to assume that the specific volume, so V for a solid or a liquid, so the specific volume for a solid or a liquid is small. So we're going to assume that this term is approximately 0 as well, because we're assuming that the specific volume is approximately 0. And I'm going to come back to this term in a minute. So this is assuming that we don't have a large change in pressure, because if dP is really large, then we can't assume that this term is approximately 0. But just for now, we're going to assume that we have a small to moderate pressure change. And so then the specific volume is really small, and so we're going to assume that this V dP term is approximately 0. So if we do all that, we get that dH is equal to du. And rewrite this a little bit better. So dH is equal to du. So we've already seen, and so now I want to go back to the specific heat equation. So we've already seen that C sub P is equal to the partial of H to temperature, and this is assuming constant pressure, and that C sub V is equal to the partial of the internal energy to temperature with constant volume. So we saw that with ideal gases, the C sub P and C sub V are strong functions of temperature, but they're not strong functions of pressure and volume. So I'm just going to write this over here. So C sub P and C sub V are strong functions of temperature, but not pressure and volume. So this was the case for ideal gases. This is also the case for solids and liquids. So the specific heats are a strong function of temperature, but not pressure and volume. So what we can do is we can change these partial derivatives into ordinary derivatives, and we get dH over dt, and this one is du over dt. So then what we can do is we can rewrite this. So dH is equal to C sub P dt, and du is equal to C sub V dt. So now what we can do is plug these directly into this equation, dH is equal to du, and so I'm just going to rewrite some of this. So dH is equal to du, and we have that dH is equal to C sub P dt, and du is equal to C sub V dt. So then if we plug these into this equation, we get that C sub P dt is equal to C sub V dt. So basically C sub P is equal to C sub V. And so remember, the assumptions for this are that this was incompressible. And we also assumed that the specific volume was very small. So this is basically can be applied to solids and liquids. And so for solids and liquids, this is just called C. And this C is the heat capacity. So basically, dH is equal to du, which is equal to C dt. Therefore, H2 minus H1 is equal to U2 minus U1. And this is equal to, from state 1 to state 2, C dt. And then we can make another assumption that this heat capacity is fairly constant over a wide range of temperatures. So we're going to say this is fairly constant over a wide range of temperatures. And so because of that, we can pull it out of the integration. If it's constant, we can pull it out of the integration. So then we get that h2 minus h1 is equal to u2 minus u1, which is equal to c state 1 to 2 dt. So this is just equal to c t2 minus t1. So this is the equation we're going to be using to solve for the change in internal energy or the change in enthalpy in a solid or a liquid for first law problems. And we're going to want to get, so we're going to be getting C off of a table, and we're going to want to get it for the average temperature. So use value for average temperature unless that's not available. So if not available, we're going to just use the value at room temperature. So if not available, use value at room temperature. Okay, so now I want to take a step back, because remember with this equation, so we had dH is equal to du plus v dp plus p dv. So this is basically the equation that we started with if I go all the way back. So we started with this equation, and this was from the enthalpy. So let's go back to that equation and look at something. So we basically, this term went to 0 because solids and liquids can pretty much be assumed that they're incompressible. There might be a few exceptions to that, but in general, we can assume that solids and liquids are incompressible. So, and then we assumed that this term was 0 because we assume that this the specific volume is generally small for solids and liquids. But we also assumed that this change in pressure was small. So basically we assumed that there was a small to moderate change in pressure. But what if there's not a small to moderate change in pressure? Then we need to consider this term for the change in enthalpy. So we basically have dH is equal to du plus v dp. So let's look at a couple of cases. Well, first of all, for a solid, this term is approximately 0. So 0 for solid. So for a solid, dH is equal to du, so we just have what we had before. So this is equal to C delta T. But what if we have a liquid? So and this is also assuming that we have a large change in pressure. So for a liquid, well, let's look at two cases for liquids. First of all, let's look at the case of constant pressure. Well, if we have constant pressure, that term is just 0, so then dH is equal to du, so then we have the same thing that we had before. So what we want to consider is the case of constant temperature. So if it's constant temperature, so basically delta T is equal to 0, then if it's constant temperature, then du is equal to 0. So then we have dH is equal to v dp. So this is equal to v p2 minus p1. So this enthalpy at certain pressure and temperature is approximately equal to the enthalpy of the enthalpy of the saturated liquid at the temperature plus the specific volume of a saturated liquid at the current temperature, multiplied by P minus P sat at the temperature of interest. So you might recognize this from an earlier chapter. So remember, for a compressed liquid, which is basically what we're looking at here. So for a compressed liquid, if we didn't have data available, so say we didn't have a compressed table to look at, we could make an assumption that the enthalpy was equal to the enthalpy of the saturated liquid at that temperature plus the specific volume of a saturated liquid at that temperature multiplied by P minus P sat. And so this equation is the reason why we can make this assumption. The problem, so the thing with this is this term is often very small, so it's often neglected anyway. And at really high temperatures and pressures, this term can actually introduce a larger error than if you just assume that the enthalpy is equal to the enthalpy at the enthalpy of the saturated liquid at the temperature. So this is just something that you need to consider if you have a liquid and you have a high pressure and isothermal, so basically T1 is equal to T2. And, this was the constant pressure. So I'm over here. So I'm just going to summarize these equations. So if we have a solid or liquid, if we assume that it's incompressible, which is a pretty good assumption for most solids and liquids, and if we also assume that there's a small to moderate change in pressure, then we could say that H2 minus H1 is equal to U2 minus U1 is equal to C T2 minus T1. If we have a large change in pressure, then we need to consider the PdV term. So for solids, dH is still equal to du is equal to C delta T. So we basically have the same thing for solids. For liquids, things are a little bit different. And then remember, this is for a large change in pressure. Generally, you're going to be using this equation, but if you have a large change in pressure, you might need to consider these other equations. So for a liquid, if we have a constant pressure, so in other words, delta P is equal to 0, dH is equal to du, which is equal to C delta T. So we still have the same thing. If we have a constant temperature, so in other words, delta T is equal to 0, then du is equal to 0, so dH is equal to V P2 minus P1. And so the way we get this, we're not going to be calculating this with a specific heat. The way we get this is, if you recall from chapter 2, so when we talked about compressible liquids, because this is basically we're talking about a compressible liquid right now. If we didn't have data for the compressible liquid, we would say that the enthalpy at the pressure and temperature that we're interested in is approximately equal to the enthalpy of a saturated liquid at the temperature that we're interested in, plus the specific volume of a saturated liquid at that temperature, multiplied by P minus P sat. So this was an assumption that we saw pretty early on that you could make for a compressed liquid if you didn't have data, is that this second term is usually really small, so often it's neglected, and at really high temperatures and pressures, this second term can actually introduce a larger error than just assuming that the enthalpy is equal to the enthalpy of the saturated liquid at the temperature of interest. So, like I said, most of the time you're going to be using this equation because you're going to be able to assume that you have a small to moderate change in pressure. But if you have a really large change in pressure, you might need to consider some of these other relations.